Okay, so recording has been started. Thank you, everyone. Good afternoon to everyone. And I would like to just introduce our speaker. We are really honored to invite Mr. Abhijit Chaudhary, Senior Data Scientist at the ADP. And this talk has been organized by IEEE North Jersey section, IEEE System Council chapter, and Fairleigh Dickinson University. And let me introduce our honored speakers. Mr. Abhijit Chaudhary is the seasoned data scientist with 20 years of experiences in software industry across multiple generations of data science, from classical statistical methods to transformer-based architectures, with a strong focus on NLP, natural language processing, machine learning, and AI-driven automation. Since the emerging of the BERT, which marked the beginning of the transformer era in 2018, he has worked extensively on real-world NLP, NLU, and generative AI projects, gaining deep hands-on experience with their evolution, promise, and the limitations. He is currently a senior data scientist uh, he's currently senior data scientist at ADP, where he has played a pivotal role across the several AI initiatives in various functional area of payroll automation, delivering high impact solution at enterprise scale. Prior to ADP, Mr. Abhijit played a critical role in several greenfield data science driven projects for leading client, including metadata smart search at JP Morgan, an early warning system at the Salesforce, credit and business strategy analysis at Capital One, and loss mitigation strategy and the risk compliance for the Truist. In addition to his product-focused data science experience, Abhijit brings a strong consulting background, having worked with the Accenture Technology Consultation and Infosys Management Consulting Services, building trusted partnership and solving complex problem across domain for leading client across the USA, Singapore, and India. Thank you. Thanks for accepting our invitation and welcome to this wonderful community and the talk. And platform is yours.
Excuse me. Uh, Thank you very much, Dr. Avi. I'm humbled to be part of this presentation. And good afternoon, everyone. My name is Abhijit, and Dr. Avi already introduced about myself. I'm currently working as a senior data scientist at ADP, the market leader in payrolls and HR solutions. And my today's presentation reflects my own views and not that of my employer. Having said that, we all would agree that generative AI has taken the world through a storm since 2022. But this revolution is not an overnight thing. It's an incremental development going from one state of the art to the next, where the current state of the art learned from the previous and modified several of the weaknesses, and the field got better and better. Although current generative AI is predominantly work like a question answering system, but the field is broad in the sense of language technology. And let me share my screen and start with a formal introduction of the topic. So you all are able to see my screen and the presentation which I have right now in front of you. Yes or
Yeah,
no?
yes, please.
Okay,
Yeah.
okay. Thank you. So my mode of presentation is rather going on the slide. I will use this view to go through the presentation. So finally, here is a formal introduction of the topic from Carnegie Mellon University, that language technology is about generating, expressing, and understanding meaning from human spoken words. So let us move to, let me allow to present the structure of today's presentation in this agenda slide. I will start with presenting a glimpse of essence or crux of how GenAI works, and then presenting representative cases where by design generative AI is great, and there are certain scenarios where it fails. And that triggers the need to understand the field holistically for several needs, introducing a unified view of language technology and understanding the need that there are cases where we need to complement generative AI with other components from different generations, and then also understand the field holistically to understand the trajectory of development till date and get a sneak peek of the potential future developments in the field. Having said that, we will realize the current state of the art has a lot to do with the role of embeddings, which is how we generate text representation in much nuanced way, generation after generation, so that computer understands and work them for a specific task at hand. And this is a common one of the common connecting chords from 1970s till date. Then I switch to I present view of the next stage, which is about neural language modeling, where we started getting word level shared understanding of the language space. Subsequently, I switched to go to the transformer era, which is the game changer, where we really started getting success in our quest for getting human-like natural language understanding and natural language generation tasks. And this is presented using both BERT as well as various GPTs, using transformer as a key underlying architecture. Before I move on, I would like to mention that in this presentation, every state of the art is itself a big topic. For this presentation, I want to touch key aspects and also highlight the applied sense and of that particular topic to build a coherent story in this presentation. And I would also like to mention that this work is primarily based on several landmark research papers which mark a particular state of the art, and it also draw from the work of few independent researchers, notably Chris McCormick, Andre Karapati, J. Alamar, to name a few. So having introduced the agenda, let me switch to my first stop in this journey, where I introduce how essence of GenAI works at top view level. Okay, consider this statement. Okay, that we have seen a sequence of word as a human, I am ordering, and then the next sequence which comes after this is complete sequence, I am ordering Chick-fil-A at chicken sandwich. Chick-fil-A is a restaurant, chicken sandwich is the thing. Our biological brain will instantly discard this statement as meaningless. Generative AI's digital brain also works in similar way. And how it does? Because it has seen very large corpus of data during its training phase, and then during that time it understood the rules of the game of language, the grammar, where is noun, pronoun, and how the words interact to generate a coherent meaning from sequence of words. There can be multiple permutation given a sequence of word, but only few are probabilistically admissible. So these are few of the things which generative AI is based upon. And here is a bit of detail. So let us consider this situation. Currently, suppose the generative AI system, seen a system till now at t equal to 0, where it has seen I am ordering. From based on this context of three words, it can go and predict the next sequence of probable words, taking any of these paths, 1, 2, 3. And then it will go on based on certain stepping criteria. In fact, that's called decoding strategy in the world of generative AI, which helps it in achieving the core task of generating human-like text. And that is delved into later part of the slide. So this is the high level working as a principle, and we can understand, we can appreciate this idea that since this is a computer system and the math has gone better and better over the years, and now a key thing is that we have cheap computing power. So this sentence, this statement from Geoffrey Hinton, who is the godfather of modern AI, who envisioned this state some 50 years back, that digital intelligence can be much, much greater than human intelligence, quote unquote, for certain tasks. Because we can have a specialized trained system that is at our disposal. So having said this essence slide, let me give you two examples. One which sketch this one good, the other bad example. So let us consider this example, which is system generated. I have created this for illustration, that there is a system, suppose chat and order, which is an app which helps people to order food at a Chick-fil-A restaurant, and there is a customer going in, and his context is that I'm at Chick-fil-A for lunch, give me a large. Okay, so in the previous slide I was saying it can branch into multiple paths. So based on the same, the system can respond in any of these sequences, and just have a quick look of these sentences yourself. You will feel that this is quite human-like and it is doing the job. You can see that it is giving very human-like three options, which serves the purpose. So the key takeaway is that when there is a conversation happening in a structured domain, ultimately this whole conversation is about generating language on top of a structured structured Chick-fil-A food menu. So everything will converge nicely in that domain. So this is thumbs up. This is really a very good use case for generative AI where it will shine. But now more important is no intent to undermine the potential of Gen AI, but this is a fact. Like there are certain situations where the generative AI fails, and those failures are categorical. Let me give you an example. The first two example where I am asking it that is this given word literal a palindrome, that does it read the same back or front, it say no, it's not literal, and that it gives some reasoning. Basically it's going in its database, converging in a semantic space, and brings a augmented output. That is what happening in the underhood, but that is wrong. It is indeed. Then I am asking it to count how many are in this word Ferrari. Since these two tasks are based on a unidirectional context of sequence, plus this is related to character level task, so by default GPT fails in this kind of situation. Furthermore, I have a maths problem here. I have given it lot of information, but intentionally I have hidden the key information. What I'm telling you, it's not very much visible on the slides, but I can tell you, I'm telling that there are two regions, East and West, Q1 and Q2 revenues. Here are the data, and I'm giving it, asking it the question that what is the total revenue of Q2? Generative AI has a tendency to not accept no as an answer. It can make some assumption and give you a very confident answer. Okay, so in fact it delusions, not hallucinate. Another example, like if I'm trying to build a name entity recognition and just throwing it some text and asking that where is name, location, SSN, generational suffix in this text, it will give me correctly most of the things, but this thing which is looking like a SSN but is not, is another example where it can fail. Ideally, this has to be separated by hyphen, and this word, this letter S in front is not admissible. So the key takeaway is, yes, agreed that this system can do excellent job in solving problems from contemporary abstract algebra, which is a text from Joseph Gallian, which is taught at PhD master's level, it can solve that problem. And I have tested it, but it will fail in a high school maths. Okay. So because it has been trained on similar text, it has developed that subject matter expertise, and it can do the job. So these are kind of takeaways. So far, I will proceed to the next part of the presentation, next stop in my presentation. Okay. So the key takeaway so far is A. Yes, it has a lot of potential, but it is not foolproof, and it demands a balanced look. What I'm trying to say in this picture is there can be a snow car, there can be a seaplane, which are marvel of technology, but they are suited for some specific purposes where and there can be certain situations where a skateboard might do the job. Not very exact analogy, but yes, by and large, that we need to have a balanced look. And when building an enterprise grade real world solution, we need to complement this technology to come up with a reliable, robust solution to get long term bliss. Okay. So then another aspect to tell it here is that, as I said, GenAI system is predominantly question answering systems from functional point of view, which are built on very high dimensional understanding of language. We will see these parts later on. And given this kind of categorical issues and concerns of cost, privacy, control, we need to have a look of the broader picture. And let me introduce this slide, which can help us in getting a step-by-step deeper dive into the broader picture. So as I said, functionally, generative AI is primarily question answering system, but the field of generative language technology has been more than that. And here are some of the key building blocks, which has been a common connecting chord across the field, providing a unified view. So essentially, the first part talks about vocabulary space. So any language is comprised of words at the basic structural and functional level. And when those words form in an admissible sequence, they start making sentences which convey meaning. So the key idea is that there is a vocabulary space associated with every language. For us, English is the language, or lingua franca, as that's called in research. So the domain specific vocabulary corpus is where we work. Then on top of that, we build a layer called embedding layer, which creates vectors on top of that language. And this is the layer which has been going evolution. And as I have mentioned, the language technology is to a very large extent the evolution of how nicely we can build computer understable embedding layers, like the base of pizza, and the toppings can come later, so that computer has the nuanced understanding of language the human have. Once we have that embedding layer ready, we can bring various machine learning and AI framework and ask this question: can you tell me what entity is this word, which document type is this new document, summarize this text and question answering. So this is the modeling layer. And this gives us a kind of way to unify this whole evolution state on state. So after this, let us go in retrospect. We will pick one kind of state of the art and then illustrate one key aspect of that state of the art. As I said, every state of the art is a broad topic in itself. So from here on, I would try to take the applied key takeaway from every state of the art and give the message that this is still underpinning in our current state of the art and helped in building a coherent journey. So let us move to our next stop in this evolutionary journey. Here I am introducing the idea of tokenizer from something from 1970s. We know TF-IDF, which has still been there. The key takeaway of this slide is this stop in this evolutionary journey is that in language technology we try to learn the knowledge which is present in certain set of documents called corpus. That is the training stage. Once we have done that learning during the training stage, we will transfer that knowledge and store in embedding layer, typically large matrices nowadays, which is called pre-trained models. But we can understand that training model gives us a vector level understanding of our domain or vocabulary space. And then once we have done this training, we can use that vector representation and model different kind of business problem and get answer to our key questions. So here is an illustration of this idea that suppose the same problem. By the way, my presentation is revolved around ordering food from Chick-fil-A restaurant, because as humans, we can really associate the story, right? That this is something common sense, and we can then add maths and computing on top of that. So here is the thing. The problem is, suppose customer is ordering food and that is going to converge on top of a Chick-fil-A menu where all the mass of convergence is lying. Suppose in the training we have this kind of orders, okay, which has happened, like give me a large french fry, give me a large spicy sandwich. All this becomes instances of training. There can be much more data like this in our training layer. And then comes the embedding layer, where the tradition is to use a program called tokenizer. Its job is to take this kind of the vocabulary space things, and on top of that do some maths, and then programmatically give you outputs which will build the embedding layer. So this example from 1970s is still a very lightweight model and can be your something lightweight need in application development. Now coming back to the topic, what I'm saying that once you have this training data ready, you do some maths on top of it, which will give you a vector label representation. The maths is captured in these slides, two terms: term frequency, inverse document frequency, number of appearances of word across documents, and the log ratio of this thing, which gives you a higher weightage for rare words, making sure they act as a signature. So without going much into that nitty gritty, the key message is passed. Let me illustrate it a bit more. So sorry about that. So this is the illustrative example following it. The output of embedding layer are few things: across generation embedding matrix, and in this case TF-IDF score. Using the learning from this training stage, whenever a new data element comes, suppose we have a order which is saying grilled chicken sandwich and waffle fry. Suppose human is not seen, this goes to a machine. What it is going to do is, based on the vectorizer which was learned during the training, it will generate a new embedding, and that new embedding is always a single row 1 times n, small n or capital N, where that n is called embedding length or dimension of the embedding. Now since we have a vector representation which we can use on our specific modeling approach of modeling level layer, and see this is programmatic output, that it is correctly telling you that what was the food item based on cosine similarity score. So this is not the main part. The main part is to highlight we generate embedding layer from which during inference, which is the major task once the training has done, we will start getting vector representations and go on our journey. The more important part is, for this particular stage in the language technology, although small size problems can be solved, but many big limitation that it in fact memorize, that whatever it you trained on, only on those type of words it will work. It won't generalize. Even it can't handle synonyms, that is, it doesn't have understanding of meaning, and it the sequence of words doesn't matter. Context of word, same word can mean different things. All those things are not catered here. So let us move to the next stage of the art, which is a very key step and which provides the bedrock for all things which followed subsequently. And this is the era of neural language models, marked by two game changers like What2Vec and Glove. What essentially it does? First, let us understand the functional part. Given given the limitation till date, we wanted to have a embedding scheme which can have a shared understanding of meaning. What that means is this classic example, that's considered two words pairs of man and king. Man and king to a human, if he thinks in gender perspective, he will think that both are very similar when considered in gender terms. Say both score very high and in same direction. Women and queen in the gender again score very high. Royalty wise, king and men, king is really royal, but man is not. But king, queen, both are gender. The key takeaway for this slide is that it's possible to have a representation of words where every word is scored in terms of various features, how much genderness in one direction it is, how much royalty it has, how much foodness it has. So that was the idea which was leveraged in the next phase, which is called neural language modeling, and it turbocharged the whole language technology space, because now the words were not as standalone things in themselves, rather they were co-located in a multi-dimensional vector space where they shared meaning, which is depicted by that. Basically, you can do a algebra, take a difference, and you do a lot of comparisons, and that turbocharged the space. And let me share the key details of how this whole thing works. The purpose is that the flow which is shown in the top is kind of more or less still there in its more advanced form, but the key functionality is still there, what is shown in here. So neural language words, the word neural is about neural networks, which helps in modeling the English language, best depicted with this example again, that I would like to order a sandwich and a large. Okay, then maybe large French fry, large whatever, large bowl of salad or whatever. So suppose there is a sequence, I would like to order a sandwich and a large. Suppose we pose this problem to the sandwich that, hey, you take a sequence of this 4 or 5 words and use that as a context and tell me what is going to come next word. Okay. So under the hood, the key nuts and bolts are that you get this input sequence, you generate a embedding vector representation understandable by the computer, then you feed this into a neural network, it take it through multiple layers and develop an understanding across the layer and spit out finally a weighted sum like this, where x1, x2, x3, x4 are the vectors corresponding to these words. And then this vector becomes an input for the next layer, whose job is to give you an output where what it does, that based on this context we provided, which is denoted by the small letter c, it predicts what could be the next target word coming from the entire vocabulary. So if we have 10,000 words, the output of this system will be a scored ranking where the most probable word comes in the top. And this is the idea, and this job is done by a technique, the maths technique called softmax, and which essentially based on log functions and related, so it will chop down the whole vectors between 0 to 1, generating a probability distribution over the entire vocabulary. And this generation of vocabulary this idea of generating a probability distribution across the entire vocabulary is a bedrock. That probability distribution is used to sample words across different technologies, different generations, which we shall see in the next slide. The key takeaways is that this whole flow using neural networks, generating this probability distribution, rank ordering the words, is still there in its more nuanced form. And as I said, these models really turbocharge the space until 2018. They remain state of the art, and then the picture really changed. It was a game-changing moment, 2018, when two groundbreaking models, one BERT from Google and then GPT from OpenAI, arrived the same year. So now the things really become very, very fascinating from 2018 onwards. So after introducing the neural language modeling, here I have another example to pass the next ideas. So since I have to cover so many interesting topics in this presentation, so I would proceed with the presentation and we can come with the questions and discussions towards the end. Or so proceeding with that thought, here is introducing the era of BERT or transformers starting 2018. I have 3 slides to depict this stop of the evolutionary journey. First, let me introduce the crux of this idea using a functional slide. Again, I am telling there is a customer who is coming to Chick-fil-A and he says, give me a chicken sandwich with a layer of American cheese on top of it. So functionally, what happens is, to a human brain, when this whole sequence comes, we don't realize, but our brain process in a way that we know that sandwich, the word chicken is kind of modifying its word, what is the next word, and how the noun, which is the pronoun associated with that noun, where is the verb, which is the
Yeah, for
object.
the
Yeah, anything I need to know, please?
Question, please. Oh, no
Yeah,
question.
I think I can proceed. Is that
Uh, there is no question, so you may continue.
yeah. So what I'm trying to say is, as a human, we know how this is conveying the meaning. Suppose this is to be understandable by a machine or program. The key idea is that every word in this sequence of words or sentence is getting some kind of attention or modification from every other words programmatically depicted by this slide and this bar chart. Essentially, the key message is that if sandwich is my target words, okay, so it gets a proportionate attention from itself as well as every other word in this entire input sequence. Few words have more attention, like chicken has more, then cheese has more, and so on, but every other word has a non-zero proportionate attention. The key idea is that this becomes a query and other words are key and value in a multi-dimensional embedding space. They interact to enhance the embedding, and that is what is depicted in my next slide. So this slide is representative for the era of transformers, although it is depicted for BERT, but the functional, I'm using the word functional working of uh, transformers is being given in a representative way in this slide. What essentially happens from a functional perspective is that if we had that input sequence which was shown in the previous slide, then when that sequence enters inside a BERT model, at the bottom of this sequence, every word becomes an input. It's not the word, but it's embedding. So as I said at the beginning, even in this is called embedding length. This is the this is the embedding coming from the pre-training layer, and this is 1 by 768 embedding, and that goes for every single word in the entire sequence, and it goes through a stacked layer of neural networks. Functionally, the job of every layer is that as this input progress through these layers, at every layer, the input words embedding gets enhanced, in the sense that it starts understanding that within that input sequence, what is the grammar happening, like which is the noun, which is the associated pronoun for that noun, which is the verb, the object, and it developed an holistic understanding of the entire language. And when at the final layer 12, there is a feed forward neural network which generates a final embedding. So when this has come out through the encoding of BERT pre-trained model, our words embedding is enhanced, and it is now captured a nuanced understanding of the entire sequence. In case of BERT, it was a bidirectional understanding, that it processed the whole word in both direction, and that is the contextual understanding that by the end it is becoming more insightful. This inner webbings depicts the idea that the words embedding gets attention from every other word which was part of the input sequence, and this whole enhancement happens in that way. So it is necessary to also introduce this slide to get a holistic understanding of this whole transformer era. So here is the thing. 2018 is the year of epoch in the entire evolution. But before that, in 2017, transformers had arrived at the scene in a paper called Attention is All You Need. That transformer was having both encoder and decoder in it, a kind of neural network which has a specific task that is just discussed now. So what happens after 2017, in 2018, that year, two groundbreaking models come. First was GPT from OpenAI yearly that year, and then in 2018, BERT from Google. And it is said, and even found in literature, that both learned from each other and had influence. So this BERT in 2018 learned from GPT. And a key idea to highlight here, that all the models on top of this blue line are generative in nature, that there is a task that they take a sequence up to a point in time, and then they predict the next probable sequences, and then they feed them that thing back in the network, and that's why they are called auto-regressive generative pre-trained transformer, or GPTs for short. So everything on top is called generative transformers. Everything in the bottom is bidirectional transformers. The bottom one only use the encoders from transformers. The top one uses the decoders. And this is a kind of timeline which is giving us in the another another idea which need to complement this slide is that this is a high level timeline, but what really happened when this system start evolving is captured to in this tabular representation. There are few things which happened in this evolution, one thing at a time, which were the key drivers or key drivers of this. Few notable things are that GPT arrived in 2018. It had a even embedding length of 768, and it had this many million of parameters. And throughout the years, the size of the model, or the parameters, that is how much knowledge is there in its embedding matrix, that size keep on increasing year over year, and that is one of the trend which is there. And then the embedding lengths also keep on increasing across every generation. So we can say that the embedding length is a kind of proxy that how many aspects of the language it is able to encapsulate. And when it was a TF-IDF, we had a set of training documents, maybe only a food menu. But in all these language model, the training corpus was not specific to one domain or one thing, but it was trained on the entire English language, like the 300 dimensional word to vec was or globe were trained on the global corpus news. BERT was trained on entire Wikipedia and encyclopedia. And the GPTs, once people learn the game that increasing the size can get us better understanding of the whole world, the training started to become more and more, and that has been a trend, and they becomes really not domain specific or vocabulary specific, but generic models in the true sense of the word. And at last but not the least, this size and embedding strategies are there, but particularly for GPTs, there is something called decoding strategy, which essentially is that once you have seen a sequence, the one which I was saying, up to time t equal to 0, where do you get next? Which path do you take in your generation journey? That part was decoded by different approaches of decoding strategy. So in this presentation, I have tried to capture the crux, and definitely those are some of the key things. So in my next part of the presentation, where I have 3 or 4 slides, which depicts the key journey of various GPTs, and I think I can switch to that part to pass the key idea of the of how generative systems starting in 2018 or in 2019 keep on evolving. So here are the key things to portray the idea. Often we colloquially say that generative AI or GPTs are about predicting the next word. Not quite true. And here is the answer why. Because if we just build a system which predicts the next word or do something more, we will keep on hitting some other problem. We'll get a bit better in our journey, but that will not serve the purpose. So here is the high level functional depiction of how a generative AI system typically works. Suppose at time t equal to 0, a customer is ordering, I would like to order a sandwich and a large. Okay. So as a human, we can think that there are certain words which can be candidate for picking the next word, which we can call next word prediction. But when this kind of system was run in practice, we started seeing that there were multiple problems. What happens that if there is a word which could be the large probability word, next word, but if you choose that word as next pick, you might be choosing a path which is not going to converge to a meaningful sequence. Like the first word may come which is having high probable, but it's not giving you a meaningful long sequence, and that will become more clear when I put these things in perspective. So it becomes that it would make more sense to predict a next sequence rather just a next word. Like if you are in this situation, you can say large French fry, and then build a stopping criteria that if you have a probability, like if you see French, all these are made up probabilities, but they convey the masses. Like the probability of the word French could be 0.42. Once you have French, then it's likely from that domain you will be picking fry. The total probability of these independent events 0.3 CIN8 and so on. The key idea is that making the next sequence prediction rather the only the next word makes more sense, appreciable with this idea. And suppose we say large bag, maybe, yeah, okay, admissible probability, but a person in this context ordering large bag of whole wheat is very, very less probable. So riding the bus of probability, it can take us places, but still what will happen that if you run this system more often than not, you will stuck into a loop. That is, you will keep on generating something like, I would like to order a sandwich and a large large French fry. That will keep on happening when you feed back the generated sequence into the network. And this is a kind of repetitive slide of the same idea that what I already talked. Okay, so this is giving that it makes sense to generate a probability of sequence. Okay, and then take it, but still we will be having the issue of repetitive text, which I just spoke a bit earlier. And this was a problem cited or found in 2019 GPTs, that it was getting stuck. So from here onwards, as I said initially, further more refinements happened, and there were few or several enhancements which paved the path, and the decoding strategy which helps us in finding the next sequence in this auto-regressive system got better and better. Two of the key ideas are discussed here. First is called beam search, that any point of time t equal to 0, just don't go about only one sequence. And since now the compute is really cheap and very fast, these things may sound too much for human, but for computers it's very easy. And that's why those lines from Geoffrey Hinton, that we can train a specialized system. So introducing beam search here, what I'm trying to say is that when you have seen a context of a given sequence at time t equal to 0, you can branch out into multiple paths, and then you can pivot your strategy in multiple ways. Maybe you will say that from here, choose next 3 or 4, 5 or 50 beams, and on that go on generating and put some kind of a stopping criteria, that when in a particular, if you take a particular path like large, then the word French, then the word toast, fry, this is more probable, this more probable, but cut still not. What I'm trying to say, from here you can branch into multiple paths. Each path will generate a total probability based on a stopping criteria, which would be a kind of probability cutoff. Okay, and based on that, which is depicted in my last slide of the presentation. So here is the thing, what I'm trying to say is, in this part, depicting that stopping criteria, and also bringing another aspect here. Ultimate goal is that the system is evolving from one state to the next, and every state has some deficiency which requires research that gets solved. So until now, even if we have reached this stage, there was a paper in 2019 called perplexity paper, called the degenerative case of neural language modeling, that the human spoken words have lot of variety. Ultimately, till now, what we are trying to pivot is that we are trying to find
वो आया था
most.
लेटर, तो प्रोफेसर ने बताया कि अब पहले करके
Yeah,
Meet, do you have question? Oh, no, it is just by mistake, I believe.
okay, okay.
Yeah.
So what I'm trying to say is, like, this paper from Allen Institutes depicts that if you use beam search or probability based, ultimately this is all sampling, probability based sampling from a distribution of words and vocabulary. Even if you pivot in on this probabilistic approach, finally you will see situations where human spoken words have lot of variety or randomness. Okay, in human spoken words, you need to give room for even very low probable words to pass through the funnel, to bring that kind of human spoken flavor. And those were randomness, and those items were pursued further in this program. Those were added in this sampling distribution strategy. And from a illustration perspective, this is an example which tells you that suppose you have this is a kind of programmatic write-up. What it is saying, that suppose you have seen a sequence of words, I would like to order a sandwich and a large. Then the next task is go into one of those branches of beam search and try to find the next probable sequence of words, and then compute the total probability of those words and put a threshold. This is called nucleus sampling. The word nucleus sampling means that most of the mass in an atom is in nucleus. It means that a language will converge, a sequence of words will converge in a very small mass. And that's what it's trying to leverage, that if we have a probability threshold of 0.9, given this much of sequence, we can sample from one of the next probable words and then choose. Once we know that next sequence of words, we will choose one word, update our sequence, and run the whole algorithm again. That's the word auto-regressive, that we will first identify the next most probable sequence, which is getting us to a cutoff of threshold, and then we will choose one word, feed back in our network, and keep on iterating this process. And subsequently, we brought randomness by adding the parameters of temperature. And that's a high level overview of the whole field of language technology, which I covered in this time. These are kind of building blocks. And here are a few research papers, which is not an exhaustive list, but as I said, that every era was marked by a research paper. But as you would also know, that now the GPT development is not kind of an open research. Previously, there was a general trend to give you a deep overview of the entire research. That was the thing till GPT-3 and all. But GPT-4 is more about benchmarking results and all. And at last, this was worked on these papers. And this is my techno-functional perspective of the entire evolutionary journey. And it was good conversation so far, everyone. It was a very lengthy topic, and I would say every state of the art is a topic in itself, and I structured it the way I had my plan. So thanks everyone, and I'm here for the next questions or whatever.
Thank you very much. Any question, please? Any question?
No, I don't have any questions.
Yeah, Daniel, please.
Professor Chaudhry, can you hear me?
Yes.
Yes.
Excellent. A question for you, maybe it's a little bit of a beginner question, but which is, if two models are being trained on the corpus, are they going to end up with the same representation? In other words, the parameter in the parameter space, the same coordinates for the same word. For example, you gave the example of king and queen and man and woman, and you showed them in a three-dimensional space, but it's of course multi-dimensional.
Yeah.
Are they going to end up in the same place, or is it completely random?
Yeah, that's a great question. So there are a few building blocks of that that question. Okay, so based on what is your algorithm, and then based on how you are implementing it, there can be differences in final learning of the pre-trained matrix. And the more probable system answer would be that they won't end in the generating the same embedding, based on what is the underlying algorithm, your training strategy. And still there would be a room of statistical randomness, and there is a stochastic process in this whole process. So
So-
at the end, the parameters will kind of perturb in a stochastic sense.
Well, let me refocus the target, and that is if I use the exact same model, in other words, the only difference is maybe the order of the training information. In that situation, how much variability will there be in the final, at the end stage of training, the coordinates of, for example, the word king? Will it be drastically, completely different, or will it be just subtle differences due to the probabilistic nature of the model?
So you kind of already answered this question, Daniel. So as you said that you keep everything to the dot very similar, and then your interest is that in a 300-dimensional vector space, the different weights which get generated for the word king, will that vary given if you have put everything accurate? As you said at the end of the question, will it vary due to the probabilistic nature of the algorithm? I would say yes, it would only have some small variations possible
good.
at
Okay.
the end.
Okay, thank you.
Yeah. Due to stochastic. Yeah, thank you.
Any more question, please? Okay, we have one chat, and this is just from the Christian. Do you think that further improve our AI would take more computing resources than we have? This is the Christian. Yeah.
Yeah, I mean, I won't be able to give really a yes or no for that, really what we want to build. But I would take it this way, that whatever advancement has happened, okay, I'm answering a bit different. Whatever has advancement has happened due to the fact that we had a very fast trajectory of high performance computing at a cheap price. That has catered to the need. But if you see from the art of possible, we can train everything, we can build multimodal systems, and whether our current compute systems, because at the end we need NVIDIA chips to be precise, do we have enough of that? There is no limit on enough. I would say there is a need of prioritization. So that triggers a thinking in myself, Christian. So I believe there is a lack, right? That is not sufficient. We need to prioritize. There is a war for super computing or high performance computing chips, and we need to prioritize. That's how I will put it.
Wonderful. Fantastic. Any more? Yeah, Eric, please.
How's it going, sir? I had a question about the weight values that were, for example, you gave sandwiches in your slides, and it gave a really high weight to itself. And I was wondering, is that for, I know you mentioned towards the end there's feedback loops where it kind of groups them together and then reruns it through it. Is that related to that, or is there another reason for a high priority for the word itself?
I hear your question. So your question is, so in that slide which I had, that was programmatically generated, and that slide was called self-attention mechanism. Okay, so whenever there is a word which is in a sequence, I'm not very ready in my RAM with all the maps, but it is that we put everything in a 768 by 68 vector space. One is query. So every word like sandwich was a query, is projected into key and value space. And based on that, based on a mother equation, the score is generated. So in all these things, the word itself will have maximum attention to itself, which is corroborated with all others. So that was coming mathematically, and it will be high to itself. That's why it's called self-attention mechanism, and it should call self-attention in corroboration with other neighbors bidirectionally.
Understood. Thank you very much, sir.
Yeah, thank you.
Daniel, please.
Dr. Chaudhry, could you speculate maybe a little bit on given that the human brain uses approximately 20 watts, not megawatts, 20 watts of power, but yet has superior reasoning abilities to any existing AI model, not nearly the same database, but it can certainly reason much better. How soon do you think we might be able to get to such power efficient model as the human brain? Any, you're closer to the research than any of us. What's your speculation?
Yeah, thank you, Daniel. This is a wonderful question. Okay, and thanks for educating me. We all are learners, a lifelong learner. So thanks for giving me this 20 watts number. So what I will say, that is a thing which is, when I presented Geoffrey Hinton's mention at the very beginning. So comparison of human brain versus digital brain, that was a topic Geoffrey Hinton was very much interested in. So to answer your question, what you are saying is that our human brain with a 20 watts of electrical power is able to make so much connections and make sense of the world. So when there would be a system which can supersede this from power and all those things, this is a open research question, but I have some directions and inputs. What I would say, again borrowing from Geoffrey Hinton, that these AI systems are in certain situations way better than human brain. Given an example, there is a number not ready with me. To do a calculation, a human brain has billions of neurons, but the AI brain has relatively later connections. But given its AI nature, it is in certain tasks, it is able to make more sense. And that's why he said that there can be digital systems which are specialized in certain tasks, and digital intelligence is much greater than human intelligence in certain tasks. And Daniel, I would also add that my example, like AI system can answer things from something in abstract algebra much advanced because they are trained there. You have the liberty to train them. But whether they will be really general intelligence, artificial general intelligence in the true sense of the word is very much questionable, because they are at the end very retrieved augmented system, right? They go into semantic space and bring data. That's how I will put. And I hope I answered some of your questions in this open research area.
Thank you. Yes, you did.
Yeah, thank you.
Any more question? So we are, extended time 5 minutes. So if you have questions, Mr. Chaudhary is going to, go ahead. Go ahead.
Hello. I was working on a project, and in that I want to run a model locally. So I was just wondering that how can we like compress the whole model efficiently without losing any accuracy on.
I think this is a very specific technical questions in area of quantization, or how I really compress. It will need a specific discussion. That's how I will put, whether there is an API based access available for that model or not. So I won't be able to answer this question at this moment, which model, what we need to talk a bit more meet.
Okay, thank you.
Any more question? Oh, no. Thank you very much, Chaudhary. And it is wonderful talk. I learned a lot, and I'm pretty sure everybody has enjoyed it and learned it. And there's no doubt you got so many questions, so they got inspired.
Yeah.
And if I'll share his email address. If you want to ask more questions, you could write him email. That would be fantastic, right? Thank you very much.
Thank you very much. It was indeed a very learned audience. I also learned, and thanks for this opportunity to share about this whole, as I mentioned, all the details in the topic. Yeah, thank you.
Thank you. Bye.
Bye. Have a great rest of the day.
You too. Bye.